have a very interesting speaker who spoke with us a few years ago. He's been studying biblical history for over 30 years. He also wrote the classic book, Thoth, Architect of the Universe, and he's written many other books since then. That came out in the 1990s when there was this big explosion in Egyptology and the ancient sites associated with that part of the world. He's recently been on the Megalithomania podcast. You can catch up with that on our YouTube channel. So we've now got Ralph Ellis is going to be talking about the dating of the megaliths, bringing in a whole different perspective, linking it with the precessional cycle. So please give a warm welcome to Ralph Ellis.
What are we doing today? We are trying to date the megaliths. We all know they're fairly old, but how old, and how can we tell how old they are? Well, one way, you've probably seen the controversy, is looking at erosion patterns. You've probably seen the debates on the Sphinx enclosure, how the amount of erosion there looks much older than 4,000 years ago. And this all comes from my books, Thoth, Architect of the Universe, and K2, Quest of the Gods. As Hugh says, this was 25 years ago I wrote these. Anyway, quite a long time ago, but all the data is still good within those books. They're outside in the bookshop if you want to pick them up. And as I say, we start this by looking at erosion patterns. So here's some erosion. This is down at Dashur, at the Bent Pyramid. And you can see here that there is a differential in erosion. We have less erosion here, where this area of the pyramid was covered up by the mortuary temple, and so the rocks were actually protected for thousands of years. And we have more erosion over here, which has always been exposed. So we can see the differential pattern. The problem with this is that we can't really get a date from this. We have nothing to compare it to, so we can't get a date. So it's interesting, but it doesn't tell us very much. But the only thing you might note is that that is the amount of erosion you get for the lifetime of a pyramid, however old that is. And it doesn't look too much, but that's because these pyramids were made with very durable Tura limestone, very hard limestone from northern Egypt. And so it hasn't eroded that much. But that's the amount of erosion you get ever since a pyramid was built. Here's some more erosion. Here we're looking at the Medum pyramid. If you've been down to Egypt, you'll probably know it very well. This is the step pyramid at Medum, and here we see a lot more erosion. So at the bottom here of the pyramid, we see less erosion. Why? Because it was covered up. What are we looking at here? Well, on the left, you see the pyramid. This is the casing blocks of the pyramid. On the right is all the debris that fell down from the top of the pyramid. A long time ago, someone suggested that this pyramid collapsed in a sort of huge, great avalanche, and that's why we've got this pile of debris sitting on the right-hand side. But when they actually did an excavation, they discovered that was not true, because all of that debris is stratified. And so what's happened is the debris has come down from the top of the pyramid over the centuries, over the millennia, and piled up at the bottom of the pyramid and protected the bottom. You see less erosion down here. But then, I think I pressed that twice. Let me go back. Okay, so we're back onto that page again. That's less erosion at the bottom. That's more erosion at the top. So you can see it's well eroded at the top. And at the top of this pyramid, as far as it goes up, it's been eroded, something like 3 or 4 meters of erosion, where the rock has just decayed away. Why did that happen? It's because this rock was much more fragile, more friable. It's only a very weak sandstone, and it's eroded very quickly. And as it eroded, all of that rubbish ended up at the bottom of the pyramid and protected the bottom. But you have to ask yourself, how long does it take to erode away a complete pyramid? Apart from the core stones, of course. The core stones at the top are made of a much harder material, so they've not eroded so much. But nearly all of the casing blocks have eroded away at the top of this pyramid. So I would suggest that it's probably quite old. Here's another way of dating a pyramid through erosion. This is back at Giza. This is at Giza. So here you see a differential erosion on the paving stones at the bottom of the Giza pyramid. So what are we looking at here? Well, this is the paving stone. They built this big platform, these paving stones, which they built the pyramid on top of. And these are made again of the hard Tura limestone, very durable sort of material. Let's have another look at another portion, the same erosion, just around the other side of the pyramid. And why do we see this differential between this area here and this highly eroded area here? It's because the casing blocks used to be on the right-hand side. So the area on the right of this image was always protected by the casing blocks and was not eroding. Whereas on the left, you can see we've got erosion ever since the pyramid was built by the feet of pilgrims, the weather, whatever is eroding it. And then, about 1,000 years ago, during the Muslim period, someone came along and stole all of the casing blocks. So now we can have erosion on both sides of this pavement. Remember, this pavement is just one block of stone. It's not two separate blocks. And so this dividing line is down one piece of stone. The thing is, with this dividing line, we get something like 10 times more erosion on the left side than we do on the right side. And that's interesting because we have this differential and we have something to compare it with. We know that the casing blocks were stolen about 1,000 years ago, in which case you could suggest that the Great Pyramid was at least 10,000 years old, based on the erosion patterns. So now we're homing in, we're getting a slightly better date for these megaliths. But here's another way of dating the pyramids, this time by repairs. I don't know if you've been down to the pyramids at Dashur. This is the bent pyramid again. And someone, at some point in time, has repaired this pyramid. So, at some point in time, somebody has covered the entire pyramid in scaffolding and sent the artisans all over this pyramid, chipping out all of the eroded blocks and putting in repair blocks. The thing is, when was that done? We don't really know. We have no idea. But I might suggest that this was something to do with Pharaoh Snefru or Snorfru. Now, he's associated with these pyramids. I mean, he's not associated in any particular way. His name only appears on some stelae outside this pyramid. But he's long been associated with the building of the Red Pyramid, the Bent Pyramid, and the Step Pyramid at Meidum. But, just as a suggestion, since we don't know who repaired this pyramid, let's just suggest that maybe Snefru is associated with these pyramids, not because he built them, but because he repaired them. If so, then the repairs have lasted for some 4,500 years. And we might suggest that the pyramid would have lasted at least that amount of time, or more, perhaps twice as much as that, before it needed repairing in the first place. In which case, we might suggest that the pyramid was constructed down here. It required no repairs for about 9,000 years. Then Snefru repaired it, and it's lasted 4,500 years ever since it was repaired. And is still in fairly good condition now if some of the casing blocks hadn't have been stolen. If that's so, then the total age of the pyramid is something like 13,500 years old. Much earlier than standard archaeology will suggest for the pyramids. But I think that's quite a reasonable date, and we can perhaps confirm that by looking at astronomical alignments, looking at precession, looking at obliquity. So, well, let's look at the first of those, which is axial precession, the precession of the equinox. I'm sure you're probably all familiar with this, but if you get a gyroscope and you put it down somewhere, it will precess. It will wobble on its axis. And, of course, the Earth is just a very big gyroscope. And so, of course, the Earth will, if it will do its thing. So what are we looking at here? Here's the Earth. Here's the axis of the Earth pointing up towards the celestial pole, the pole of the Earth. And in the center here, we have the ecliptic pole, which you might think of as the pole of the whole solar system. And obviously, they don't point in the same direction. And so we get this difference between the two. And the celestial pole, as the Earth wobbles, goes around the ecliptic pole. And so it draws this nice big circle in the heavens above. And now that's useful because perhaps if you're aligning your megalithic monument with something like the sun or the moon or any other of these celestial objects, you might be able to get some sort of date out of it. Where do we get this information from? We get it from Lascar, Monsieur Lascar, based in Paris. And he's compiled data for this for the last 20 million years. So it's a nice regular pattern we can use for dating something. And you can take his data, and you can draw a nice little diagram. It's supposed to be a bit more of a sawtooth than this, but the pattern is correct. I'll have to adjust this later. And we get precession. So down the bottom here, we've got dates. We've got 0, that's today's date, 100,000 years ago, down the bottom, and the angle of precession. And this is a 26,000-year cycle. So we get this regular ticking of a clock, this regular metronome ticking away. And, of course, we can use the ticking of a clock to do some dating. So, well, let's see what we can do with it. Well, one of the things we can do with it is we can have a look at paleoclimatology. I don't know if you know, but I've written a science paper, peer review science paper on ice ages because I was a bit concerned that in the 21st century we don't know how ice ages are modulated. We had a rough idea, but we had no idea how they were fully modulated. So I wrote this paper, and it's been, it's called Modulation of Ice Ages via Precession and Dust Albedo Feedbacks. We're coming back to precession here again. And it's been very successful. It's been downloaded some 45,000 times, which is not bad for a paper. And it's been controversial because it doesn't use CO2 as a feedback. Highly controversial. It uses dust albedo instead, the reflectivity of ice sheets. Now, we're not going to discuss this today, but it's going to come in at the end of this talk, just very briefly at the end of this talk, because I got a little bit of a shocker for you at the end of the talk about ice ages. Anyway, so enough of that. We're going back to the megaliths, and we're going to draw a little pattern here. You're probably familiar with this, I don't know. What are we talking about here? Well, let's put some names on this. We're talking about the Giza pyramids, going down to the Red Pyramid, and then down to the Bent Pyramid. And we set up this pattern, as you see on the screen there. And I think this pattern is useful. It's deliberate. It's not by accident. And the angle, the obtuse angle here we're looking at, is 191 degrees. I think that represents something, partly because it's 11 degrees displaced from a straight line. And if you know anything about the Great Pyramid is based on pi, 22 over 7, or 11 over 7, half of pi, or 5.5 over 7, quarter of pi. And so the number 11 occurs quite often within the Great Pyramid, and here we have it again. So what is this pattern? What am I thinking that this represents? I think it represents this, a series of stars and points. So what's this? Well, let's put some names on this as well. We have Orion, the ecliptic pole, and the celestial pole, just as we've been talking about previously. And if you remember from the previous diagram, the celestial pole goes around the ecliptic and it forms that yellow circle in the heavens above. Here's the yellow circle. And so, because the celestial pole rotates around the ecliptic. Now, you can put this onto a computer planisphere and you can adjust it left and right a bit until it equals our 191 degrees here, which we seem to have from Giza and Dashur. So let's do that. Here's our 191 degrees. And that's interesting. Why are we interested in this? Is because you can make a date from this by adjusting it, and it's pretty accurate. It's like plus or minus 10 years. You can take a date from the position of the celestial pole. And that date is 13,500 years ago, 540. Now that's a little bit older than you might expect for the Giza and Dashur. They could be 13,000 years old. And why else would we have this layout? You know, if that's what the designer was trying to represent, that's the date you get. Okay, it might be a bit older than everyone is expecting, but that's what the imagery gives. Can we confirm this? Because we like confirmation, otherwise it's just speculation. I think we can confirm it because we have the standard method of dating at Giza, which you've all probably heard of before, which is precession spotting using the Sphinx. So what's the Sphinx doing? The Sphinx is looking due east at the vernal equinox, the spring equinox, and it's looking for itself coming over the horizon. Here's Leo coming over the horizon, and that gives us a date. And you're probably familiar with it, 10,500 BC. It's not quite that, though, because remember, Leo is quite a big constellation, so we get anything between 10,000 years ago and 12,500 years ago. That's the one you're probably familiar with, 10,500 BC. So what I'm doing is taking the median in between those two, which is 11,250 years ago, which is old, it's interesting, but it's not the same date that we've just achieved using the layout of Giza. So what's the problem with this diagram? I think people have been looking at the wrong date, because if we look at Giza from above, here's a nice satellite image of Giza. What they've been doing is looking due east at the vernal equinox. And here is, because it's difficult to see on there, isn't it? Anyway, here is the Sphinx, and the Sphinx is looking due east at the vernal equinox. But that's not what this layout is really showing us. if you think about it logically, what it's saying is we're looking at 14 degrees to the right. If you wanted to look due east, you would have done it down here on the third pyramid causeway. But it's not. It's looking down here. And that's a very particular angle. It's called the cross quarter. It's not just any old angle. It's 14 degrees from the vernal equinox, which represents one calendar month. So instead of looking at March the 21st, we're looking at February the 19th or 20th. Different date. And so what we've got here is on February the 19th, we're looking due east, because the Sphinx is looking due east, at Leo coming over the horizon. All very interesting, but it gives us a different date. And so that date is, oh, there's my little box. Where's the date? At the cross quarter, it's 13,500 years ago, which happens to be the same as our layout date that we've just seen, which was 13,500 years ago. So we have a sort of confirmation here by two different methods of looking at precession at the Giza pyramids. We end up with the same date. So the suggestion is that the Great Pyramid and the Dashur pyramids, of course, were built 13,500 years ago. Quite a long time ago. Not too much older than the 10,500 that people have been claiming, but certainly much older than the standard archaeological date of 4,500 years ago. Can we confirm this? Because we like confirmation. Where else would we find a megalithic monument that is aligned to certain astronomical events? I might suggest something like this. And we've got two. We've got Stonehenge and Avebury. Avebury tends to get forgotten in all of this, but I think Avebury is rather central to this. So who's been looking at this? Well, lots of people over the years. The first that I found is Flinders Petrie, 1880. And he was using precessional dating on Stonehenge. So that's quite a long time ago. The only problem was Flinders Petrie got his precession round the wrong way. And so he ended up with a date of 600 AD. That's why you have all these ideas that Stonehenge is post-Roman. It's because of Petrie. And then Lockyer came along, 1900, and he said, sorry, Petrie got his precession round the wrong way. It should actually be like 1600 BC. So that's Norman Lockyer, and he did a very good survey of Stonehenge as well, which is quite a good survey. And then Atkinson came along in the 1950s, and he said, sorry, Lockyer's survey was all wrong. It's all displaced by 1/4 degree, so it's not quite accurate. So he did another survey. And then we had Gerald Hawkins, professor of astronomy. I think he came from America, I'm not sure. Anyway, a very renowned professor of astronomy. He came along and did lots of astronomical alignments. Didn't really look into precession very much, which I was a bit disappointed about. And neither did Atkinson. Atkinson, I thought, left out a lot of information there. He said we don't have to look at precession because we've got carbon-14 dating. And so he didn't do any. So I think he missed a trick there. What we need is confirmation. You've got carbon-14 dating, but, can we try and confirm it, please? And then after Hawkins, we get Prof Hoyle, another astronomer, renowned professor, who did another great book on Stonehenge, looking at the astronomical alignments. And then, of course, we had Alexander Thom, who did a good survey of a lot of these megalithic monuments. They were sort of looking at precession. They were not looking at obliquity, as we're going to do. But I want to go beyond Petrie, beyond Alexander Thom, and look at all of the possibilities that they did not look at. So we're going to go right out on a limb here and look at something that's completely different. So they mainly looked at precession. We are going to look at obliquity. So we've seen precession. Precession is the Earth wobbling on its axis, and obliquity is just the tilt angle, backwards and forwards, because the Earth's angle of tilt changes. And so it goes from a minimum of 22.1 degrees all the way up to 24.4 degrees. It's 2 degrees, more than 2 degrees of tilt change. And of course, we can get the data. Who do we get the data from? Oh no, we're going to look at Avebury next. So the data comes after this. So Avebury, where might we find obliquity on a megalithic monument? Well, I would suggest that we might find it at Avebury. So Avebury, I'm sure you're familiar, huge, great megalithic monument, 400 meters across, so big it has a village inside it. And of course, in the center of Avebury, most importantly, we have the Red Lion pub. So it seems quite obvious that the pub was built first and then Avebury was built around the pub. You've got to get your priorities right, you know, in this megalithic architecture. But what is Avebury? I mean, why did they go to the trouble of making this enormous, great megalithic monument? What does it represent? What did it represent to the designer? Well, what do we have? We have an enormous, great circle with 4 entrance gates, sort of north, south, east, and west. What does that look like? Well, I think it looks like this. It's an image of the Earth drawn on the plains of Wiltshire. And of course it has an axis. And that axis is at 22.5 degrees from due north. And the Earth could be as well. We'll look at this in a minute. And it has an equator. And that angle of 22.5 degrees is well within the limits of the Earth's obliquity. We've already seen on that diagram that obliquity goes from 22 degrees up to 24.5 degrees. And so an obliquity angle, which we see here, the leaning angle of Avebury, is well within the limits of what we get for the real Earth. So what I'm suggesting is that the designer knew the angle of obliquity of Earth at that time and included it in the design of his wonderful great megalith, his huge great henge, to preserve that knowledge for future generations. But that's interesting because it's not only demonstrating that the designer had much more technical knowledge than we would give them credit for, it also gives us a date. So how do we get that date? Well, we go back to Lascar, which I was going to go on the last page, but here he is. We get that data from Lascar again, Monsieur Lascar over in Paris, who's calculated obliquity for the last 20 million years. And from that data, we can draw another little graph. So what do we have here? Down the bottom, we've got dates again. So here's 0, that's today's date. Here's 100,000 years ago, just because I wanted to go back that far. Here's the angle of obliquity, all the way from 22 degrees all the way up to 25 degrees. And you see this nice little sine wave. Another nice, regular metronome, ticking away slowly. How slowly? It's a 40,000-year cycle. Again, a nice ticking clock with which we can date megaliths, a regular 40,000-year cycle. Can we prove that, because I drew this, this graph, I put it into a graphical program and drew this. Can we check that it's correct? Yes, we can. We can put today's data in. So here we've got the modern obliquity. All we do is we chase down the purple line until we hit the blue line, drop down a perpendicular, and it comes out with today's date, which is 0. So that data is correct. But of course that angle there, 23.4 degrees, is not the angle of Avebury. What do we find at Avebury? Well, we find 22.5 degrees. So here's the Avebury angle of obliquity, 22.5 degrees. And you see it cuts much lower. It's a degree less than modern obliquity. But that might give us a date. How do we find the date? Well, we go along the blue line until we hit the dark blue line, until we hit this line. So let's have a look at that and draw our first date on. So there's the intersection, drop down a perpendicular, and we get a date of 24,000 years ago. And that's the first date going back into the past that we arrive at, because, here's the current date here. That's the first one we come across, is 24,000 years ago. What that is suggesting is that Avebury was built 24,000 years ago. A lot longer in the past than most people would give it credit for. And we'll look at the implications of that in a minute. But we don't have to stop there. Why stop at the first, part of the sine wave? We can go back further in the past. So we can go back to another point. Let's drop another perpendicular. How about that one? We've got 33,000 years ago. And we can go back even further if you want, if you want to really go out on a limb. And here we get 66,000 years ago. And finally, the last one I've got on this graph is, it didn't work. Let's do that again. 74,000 years ago. So take your pick. You've got a whole series of dates. We've only got 4 dates that it could possibly be. If this was the idea behind the designer of including that 22.5 degree obliquity angle for Avebury, these are the 4 dates that you get. 24, 33, 66, or 74,000 years ago. But we like confirmation, so where can we find confirmation of any of this data? Well, maybe a site like this, because we know Stonehenge has various astronomical pointing aspects to it. So what will Stonehenge tell us? Well, let's have a look at Stonehenge, shall we? Here is Stonehenge from above. Nice picture, highlighting all of the aspects of Stonehenge, but we're not really interested in the stone part of Stonehenge. That's sort of like a glistening bauble to sort of distract your attention. What we're interested in is the earthen henge that goes around it. And what we're also interested in are the 2 smaller henges inside. We've got one here and one here. You'll see it on the next diagram. You can't see it so well here. So let's mark those. Okay, it's gone on to this one. Okay, so what are we looking at when we see those designs at Stonehenge? I think we are looking back at precession again, same as we saw before. So you've all seen this diagram just a minute ago. And so this is the Earth precessing on its axis and forming this big yellow circle in the heavens above. So this is the celestial pole rotating around the ecliptic pole and making this big yellow circle in the heavens above. So if you go out on a winter's night, you'll see this big yellow circle in the northern skies. And that's important. So remember that, because when we start looking at Stonehenge, what do we find? Here's Stonehenge from above. This is an infrared image, which is nice because it depicts the henge quite well. And what is that imagery? I think it's based on precession, as we've just seen with the Earth precessing in space. So let's replace the Stonehenge with an image of the Earth. Here it goes. And let's highlight those little henges to the north and south, so you can see those. What is this imagery? I think it's the precession of the Earth. And so we can draw that on. Here's our yellow circles, which will be in the northern heavens and in the southern heavens, of course, because the Earth is precessing on its axis and it's drawing that big circle in the heavens above. And so, well, I suppose we can animate this and have a look at it and see what it does. So here's the Earth precessing on its axis and drawing those circles to the north and south in the heavens above and below. And that's the imagery that Stonehenge is giving us. What else can it be? Why have those two little henges here to the north and south if they are not marking the precession of the equinox? But that's interesting again, because not only is that demonstrating that the designer understood the precession of the equinox and could draw it on a megalith, thousands of years ago, but this size of these circles to the north and south is dependent on the obliquity of the Earth. So as obliquity changes, that circle gets bigger and it gets smaller by 2.5 degrees as the obliquity changes. And so if we can calculate the size of these circles, then we can get another date, much the same as we did for Avebury. So let's clean this up and go back to the original image. Okay, we're back to Stonehenge. So let's look at a diagram of Stonehenge and see if we can calculate how big those circles are. And it doesn't really matter how accurate the actual artisans were on the site in making this site, because the designer has left us a calculator, in fact 2 calculators, to calculate exactly how big these little henges are. So let's put the Earth back in the center again, as we had before. So here's the Earth. And how can we calculate the size of those yellow circles? I think we can do it by looking at the Aubrey holes. If you're familiar with Stonehenge, you will know that there's a ring of holes all the way around the perimeter, known as the Aubrey holes. And they have no real function. They're just there. It's not even really known if there was any, tree stumps or stones actually in those particular holes. They don't seem to have a function. What is their function? I think they are an obliquity calculator, basically. So, Aubrey holes, we've got 56 holes within the perimeter, within 360 degrees. And that means that every hole is displaced from its partner by 6.43 degrees, which might seem an odd number that has no particular significance. But between these station stones, here are the station stones, 1, 2, 3, and 4, there are 7, excuse me, there are 7 of these Aubrey holes. And we're looking at half of that, so we're looking at 3.5 Aubrey holes. And it just so happens that 3.5 Aubrey holes is 22.5 degrees, the same as at Avebury. And so what we might suggest then is that the Stonehenge obliquity, the tilt angle of the Earth that is relevant to Stonehenge, is 22.5 degrees. But there's more, because there is even more confirmation. So the designer, when they designed Stonehenge, they put in a Pythagorean triangle. And you probably all know this if you've read any of the books on Stonehenge, but the station stones, these ones marked with the number 3, form a nice rectangle, and within that rectangle you get a Pythagorean triangle. And as you know, Pythagorean triangles, there's not many of them. So they're pretty rare, and it's demonstrating that the designer understood the principle of Pythagorean triangles. And so we end up with this triangle, which is a 5, 12, 13 Pythagorean triangle. And that has a specific angle. It has an angle of 22.6 degrees, which confirms our 20. That's the closest you can get with Pythagorean triangles to 22.5. It's another confirmation that they were looking at this special angle of 22.5 degrees. And if you want to know how big Stonehenge is, this, I would suggest, was built in megalithic yards. So this is a confirmation, I suppose, that Alexander Thom was correct when he calculated his megalithic yard for all of the megaliths. If you want to know how big this is, this line here is 40 megalithic yards. This one is 96, and this one is 104. And you might think those are very odd numbers to have for a triangle, but if you divide by 8, you get 5, 12, 13. It's confirmation that the megalithic yard was being used on this site. And so we end up with this angle, this special angle of 22.5 degrees. And of course, it's the same as we find at Avebury. We have a triple, as it were, confirmation that this angle is special. And it's, as far as I can see, this is looking at the size of that big yellow circle in the heavens above, and that will give us an angle of obliquity. So let's draw that graph again. We've seen it before. So here we've got dates on the bottom. This is the 0 date, going back 100,000 years, and here's the angle of obliquity on the left. And we can draw those same points that we saw on previously. So let's quickly draw those on. This time, though, this is for Stonehenge and Avebury together, because they confirm each other. And we get our 4 dates. So those are the 4 possible dates we get for Avebury and Stonehenge. Again, a lot longer in the past than most people would credit these megalithic monuments with. Can we confirm this? Because we like confirmations. The only way I can think of confirming this is maybe compare it to Giza. And of course at Giza we ended up with a date of, let's put the Giza date on there. We ended up with a date of 13,500 years ago, which is not the same. So a little bit disappointing that we don't find the same sort of date, but there you go. That's the data as it's presented to us. But, there's always a but, we don't have to stick with just the first part of the sine wave for the precession of Giza. It's a sine wave. It continues ad infinitum, going back into the past every 26,000 years. And so we could, if we wanted to, look at the previous dates that might come out of Giza. And they are 39,000 years ago, 66,000 years ago, and if you really want to go out on a limb, 91,000 years ago. And we do have a correlation. Not perhaps one that you or I expected, but we do have a correlation just here. So let's draw that graphically, because I think it's easier to see on a table rather than in that format. So here's my table of what we've discovered so far. So on the left here, I've got thousands of years, before present, going from 0 up to 100,000 years ago. And on the bottom, we've got the 4 things we've looked at. So we've got the Sphinx, the Giza layout, the Avebury obliquity and the Stonehenge obliquity. And we can put on those various findings that we had. So these are the first four. These are the youngest ones. So we've got 13,500 years ago here and 24,000 years ago here. But we don't need to stick with those, of course. We can go back further in the past to one of the previous parts of the sine wave for obliquity and for precession. And we get these ones. And we can go back into the past even more. And we get these. And then if you want to go out on a limb, you can be really old and go back 90,000 years. Whatever takes your fancy. So what do we make of this? Is any of this data valid? Well, it's your choice. You know, this is the data as it's coming to us from these megaliths. And the youngest of these, which personally I think is the more reasonable, is this. So what this is saying is that Avebury and Stonehenge were built first, 24,000 years ago. And then there was a sort of like a 10,000 year hiatus for some reason before they came back again and built the Giza pyramids 13,500 years ago. You might suggest that's why, you know, the Giza pyramids are more technical than Stonehenge and Avebury, but, you know, who knows? But if you want it as one grand megalithic era and one grand megalithic project, then you have to go back to 66,000 years ago. Yeah. Can a pyramid or a henge last for 66,000 years? That's the question. Or even 24,000 years if you want to go back that far. Well, Giza, the Dashur pyramids, they work encased in very, very tough, durable Tura limestone, which could withstand thousands of years. When we know it's withstood, you know, at the very minimum, something like, you know, 5,000 years, possibly 13,000 years. Could it have lasted even longer, 66? Well, we have nothing really to compare it with. It would be nice to have, you know, a monument we know with a certain date that we could compare the erosion patterns with. I don't know. I think it's stretching it a little bit, you know, to take it back that far. And what about these ones, Avebury and Stonehenge? 60,000 years? Well, the sarsen stones will last that long, no problem. It's a very hard silicate sandstone. They will withstand 60,000 years, no problem. The problem is the henges. So the ditch and bank of the actual henge, which will obviously erode and fill in over the millennia. But if you would postulate that someone was coming along every 50 years or every century and digging out the ditch and remaking the bank, of course, then the henge would last as long as you want. And the state we see it in at present is only due to the abandonment of those sites when they weren't being cleared anymore. So it's possible, if you could speculate that someone was looking after these sites, that Stonehenge and Avebury could have lasted a lot longer than we think. And carbon-14 dates, I would tend to disregard most of those, because most of those are from artifacts that have been found at the bottom of the henge ditches. But of course, if you're keeping your ditch nice and clean, there shouldn't be any artifacts at the bottom for you to date. So the fact that you found something in the bottom of the ditch represents when the henge was abandoned, not when it was built. There is no correlation between finding something in a henge and saying that was the construction date. No correlation whatsoever. So a lot of the carbon-14 dating, I would tend to disregard. Unless you can find something underneath one of the megaliths, one of the uprights of the standing stones, then you could say that that is coincident with the building era of the megaliths. But when they did move some stones at Stonehenge, they didn't find anything at the bottom of it. So there was nothing actually to compare and carbon-14 date when they removed the stones. The other question you might ask is, can Stonehenge and Avebury have survived the Ice Age? You know, if we're talking 24,000 years ago here, 66,000 years, this is the center of the Ice Age. The Ice Age didn't break until about 17,000 years ago. And the ice didn't recede until about 10,000 years ago, fully recede. So we're in the middle of the Ice Age here. Could they have withstood the Ice Ages? Well, here's the Ice Age. So here we have Britain covered in ice, and we know exactly where this ice terminated. You can see how intricate that end of that, the terminus of the ice is. We know where it ended because we have the evidence. We have the drumlins underneath the ice. We have the drop stones and the erratics, they call them, the stones that were dropped at the edge of the ice sheets, the terminal moraine, the scratches on the hills. So we know exactly where this ice was and where it wasn't. And that is the terminus of the ice sheets. And Stonehenge, of course, and Avebury, they're here. So they're clear of the ice sheets. And if you want to look at the building of the henge, the Precessional mountains are clear as well. So you can even go and collect bluestones if you want. They're all in the clear. The only ones that aren't, of course, is anything that's up in Scotland or anything that's in Ireland has to be post 11,000 years ago, because they were covered in ice, they would have been destroyed. So any of the megaliths up here are more recent. But, I mean, they were only doing what we have done since the medieval era. People in local towns, they went to the big cathedrals, they saw this enormous great cathedral down in Salisbury or wherever it was, and they wanted a smaller cathedral in their town, so everybody built a church. And they did exactly the same here. They all came down to Stonehenge and Avebury, they saw how wonderful these monuments were, and so they went back to their own local town and they built a small henge. And so we see this great proliferation of smaller henges all over the country as the ice sheets receded. The other thing you might think about is, what would the weather be like for building these sort of constructions? Well, during the Ice Age, it was 12 degrees cooler at the poles than it is now. Not down in the tropics, it was only about 2 degrees cooler in the tropics, but at the poles it was 12 degrees cooler. So here, the latitude of Britain, it was probably something like 10 degrees or 8 degrees cooler than now. It was pretty chilly. You would not want to be up here during the winter. It would be very inhospitable. But during the summer, well, it's like going up onto the tundra now. During the summer, you know, the brief 3 months of a tundra summer, it's quite balmy. There's animals, there's wildlife, there's insects, there's grasses, there's everything is growing. And that's what it would have been like here. Even more so at this latitude back in that era, because here's the little secret that people won't tell you about, and it prevented a lot of work on paleoclimatology for many years. And the secret is that 60,000 years ago, the sun was stronger than it is now. So there was more heat, there was more sunlight during the Ice Age than there is now. And here's my graph from my peer review paper. And what's it showing here? Well, it's showing temperature in red, and it's showing the strength of the sun, you might call it, insolation, how warm the sunlight is. And that's in blue, going up and down. Now, here's us here. So this is years down the bottom here. This is thousands of years before present down the bottom. Here's 100,000 years before present. And here's the strength of the sunlight, going all the way from 420 to 520, measured in watts per square meter. And here's us here at 480. And if you go back 50,000 years, it was even stronger. It was 10% stronger then than it is now. And that was a great stumbling block that stopped research on ice ages, because people didn't fully understand how you can have an ice age when the sun was actually stronger at these latitudes. And the reason is albedo, of course, but we're not going to look at that. But the thing for this sort of investigation is that during the summer, the sun at this latitude would have been stronger than it is now. So it would have been quite balmy up here during the summer. I mean, the ice sheets would only just be 100 miles north of here, but it would be fairly balmy. So you could come up here on a pilgrimage, you could visit Stonehenge and Avebury during the Ice Age, have a very pleasant couple of weeks, and then go back south again. And that would be entirely possible. And we know that people were up in this area at a very early date, because we have those pits from Stonehenge that Hugh was talking about earlier, which have been dated to 10,000 years ago, which is only just after the Younger Dryas. So yes, people could have been up in this region during the Ice Age, either making or certainly visiting and venerating Avebury and Stonehenge. So what's the conclusion? Well, whether you like it or not, the megalithic era, by this precessional and obliquity dating, is either 13,500 years ago for Giza, or 24,000 years ago for Avebury and Stonehenge. Or if you want them both as a grand building project, we're talking 66,000 years ago. So that's something to think about. And that is the end.